Hi, I'm Charlie Sitler. I teach math at the Beekman School, and I'd like to show you a few things about geometry and algebra. And I would like to show you how the procedure for squaring a binomial can be demonstrated geometrically with, of all things, a square. Okay, now we're going to see that the algebra of squaring a plus b and the geometry of forming a square of side a plus b can get along just fine. We are going to square a plus b as our first order of business. What it means to square something is to multiply it by itself. A plus b is a binomial, so we're going to multiply a plus b times a plus b. It's a binomial times a binomial. Anytime you multiply a binomial times a binomial, you want to use FOIL as a memory device. F stands for the multiplication of the first elements in the parentheses. So we get a times a is a squared. O stands for the multiplication of the outer elements, the very front and the very back element. So we get a times b, ab. I stands for the multiplication of the two inside terms, the inner terms. So we get b times a, which is ba, which is also equal to ab. By the way, it should come as no surprise that when you square a binomial, the o and the I terms will be exactly the same. And then L stands for last or ladder. We multiply the two last terms together and we get b squared. These are our four partial products that the memory device FOIL gives us, and then we collect them up. Collecting like terms, we get the formula, a squared plus 2ab plus b squared. But rather than just memorize that as an algebraic formula, let's try and see how we get that from two-dimensional geometry. We use the nickname square for raising to the second power because we live not just in 2 dimensions but 3. Right? We also have the nickname cube for the third dimension, raising to the third power. But a square is what a segment would be if it could live in 2 dimensions. So here's a one-dimensional segment. Let's move it up into 2 dimensions at right angles, and now we have something that has an area. Let's see what that area is, but let's cut it up like a jigsaw puzzle first. Each side has a, length a plus b. A is considerably longer than b, just so we can keep track of things. A plus b, a plus b, a plus b. We have notches where the length a meets the length b. I'm going to connect them. Segments. Segment here and a segment here. These segments are parallel to the sides of the square, so we continue to get right angles in each case. And what we have here is seen to be a smaller square with side of length a. The area of portion 1 will be a times a, or a squared. This corresponds directly as an area to what we came up with as an algebraic expression for our f. Over here we have a slender little rectangle. It's got one side length b and the other side length a. It has area AB. This could correspond to the expression 2 in FOIL, the O expression. Down here we also have a slender little rectangle, side A and side B, again area AB. This area corresponds to the expression AB, which is the third element in the FOIL, the I expression. And down here we have a tiny little square, side B times B for area B squared. This fourth piece in the jigsaw puzzle corresponds to the fourth entry in FOIL, the L multiplication, which gives us b squared. Now, the area of this entire square is going to be the sum of the 4 different areas, just like a jigsaw puzzle. A squared plus AB plus AB plus b squared. Collecting up our ABs, the area here is seen to be identical with the expression we got when we squared a plus b algebraically. A squared plus 2ab plus b squared. And what happens in the ballpark of geometry in no way conflicts with what's happening in the ballpark of algebra. I'm Charlie Sitler. I teach math at the Beekman School. I want to thank you for your time and your attention. I wish you well. I look forward to seeing you again. And until then, ciao.